We will now begin the second part of Lecture 24. Here we're going to do lots of examples and sample problems, beginning specifically in polar coordinates, and then broadening our consideration so that we consider integrals of any of the types that we've studied so far, double integrals of any of the types that have so far been studied. So we'll begin with an example. Let z be the surface 1 minus x squared minus y squared. Find the volume between the surface and the unit disk centered at the origin. So as we begin the solution, it's fairly clear, hopefully, that this region is of circular nature and is going to be best represented in polar coordinates. We are, however, going to begin this example by attempting to compute this integral in Cartesian coordinates just to see how bad it gets. And we'll quickly back out, reformulate the problem in polar, and see how much nicer it is when the proper setting is utilized. So in Cartesian coordinates, the unit disk centered at the origin is described as a type 1 region in this way. It could also be described as a type 2 region, but to describe it as a type 1 region, we're letting x go from -1 to 1 on the x-axis. And for each of those x values, y is going to go from the lower curve here, which is the lower half of the circle, unit circle centered at the origin, to the upper curve, which is the upper half of that circle. So we've got our y values going from the negative root to the positive root that describes the circle as a function of x. We can now set up the double integral with those limits of integration. So the double integral over d of this integrand is going to be the integral x as our outermost integral. The limits are -1 to 1. And for y, we're going from the lower curve to the upper curve here. Forget the dA term that I had to cross out there. I'm taking an antiderivative with respect to y and getting y minus x squared y minus 1/3 y cubed. And y is going from this negative root to this positive root. I plug those limits of integration for that inner integral in, and I end up with something that's fairly bad looking. This is going to be twice this root minus twice this product, x squared times the root of 1 minus x squared, and then minus 2/3 of this expression to the 3/2 power. You'll see that the signs all line up nicely, and that's why I'm doubling each of these expressions when I combine these. And now I'm supposed to integrate this with respect to y. I don't actually know how to integrate any of the three summands here. I'm sorry, with respect to x, that should be. So that's a typo. This is an integral with respect to x here. But I don't know how to integrate any of these three summands with respect to x. So this thing is already looking bad. Let's back out and let's try it in polar and see how much nicer things are. So in polar, D is just a polar rectangle. We're letting theta go from 0 to 2 pi because this region has its full circular symmetry. It takes all values of theta are allowable, so theta from 0 to 2 pi. And then r is going from r equal to 0, which represents the origin, out through r equal to 1, which represents the edge of this disk, the unit circle centered at the origin. So D is a polar rectangle, and in place of all those elaborate square root expressions, I'm just going to have constant limits of integration for all of my integrals when this iterated integral is performed in polar coordinates. So the volume we're interested in is the integral over d of the surface with respect to area. As an iterated integral in polar, we're going to pick up our r, dr, d theta expression for a, dA. I've got my 1 minus, here's x, r cosine theta squared, and here's y, r sine theta squared. R is going from 0 to 1, and theta is going from 0 to 2 pi here. The r cosine theta squared minus r sine theta squared minus r cosine theta squared minus r sine theta squared just simplifies to r squared. You can see that either by taking this square of the product, writing it as the product of the two squares, so I can write this parenthetical expression as r squared minus cosine squared. I'm sorry, r squared times cosine squared, and here I've got r squared times sine squared. Factor the r squared off, and use the trig identity that says cosine squared plus sine squared equals 1. That's one way to do it. Another way to do it is to back up a little bit and recall that x squared plus y squared is always going to be r squared. So you need not actually substitute x as r cosine and y as r sine. Instead, you could make the substitution that x squared plus y squared is just r squared, and that'll save you a bit of time. Both are fully valid. Generally, if you start to see these sum of squares involving your rectangular variables, it's good to start to recognize that that's just r squared. That's the quicker way. So this whole parenthetical expression simplifies to 1 minus r squared, and we've got this extra factor of r that was introduced from our dA expression because we are working in polar. So I can distribute that across. I can take an antiderivative with respect to r. This is all just a polynomial. I can plug in 0 and 1 and have 1/2 minus a quarter here. And the integral of 1/4 from 0 to 2 pi is just going to be 1/4 times 2 pi, which gives me pi over 2 for the final answer. So an integral that got prohibitively bad in Cartesian became relatively simple in polar. That's because the integral that we were integrating, the region rather, that we were integrating over was a circular region. Trying to express it in rectangular coordinates involves many square root expressions, which generally they can get fairly entangled fairly quickly. But expressed in polar, it was a nice rectangular region, and it was integrated simply. So let's have you do a problem. Find the volume below this cone and above the given ring. So you're going to have to think about what the region looks like. You're going to have to think about how to find the volume below a surface and above a portion of the xy plane, and set up the integral however you see appropriate. So give that some thought. Feel free to look back at examples, and we will reconvene in a moment. Alright, everybody should have time to pause the video and attempt the problem, so let's actually have a look. Let me say really quickly that I recognize you may be just watching these videos and be feeling lazy at home and want to just watch me do it and not actually attempt it. I do recommend you sit down and do these with pen and paper, when to watch these videos with pen and paper, and actually do attempt these sample problems. You're not going to get half of the use out of these lectures if you're not trying the sample problems before looking at the solution. I've said it before, I'll probably say it again, but do actually take the time to work on them. Alright, now let's look at the solution. So our ring was the xy pairs such that x squared plus y squared were between 1 and 4. X squared plus y squared equal to 1 gives me the circle of radius 1 centered at the origin. X squared plus y squared equal to 4 gives me the circle of radius 2 centered at the origin. So we're talking about the region between those two circles. That's what R is. I've drawn it here. And in polar, that's telling me that I want R to be between 1 and 2. And because this region has full circular symmetry, all values of theta are welcome here. So theta is going between 0 and 2 pi. Another way to think about this, my favorite way to do these, is to draw the region and then think about r and theta. You can also say that from this expression for the ring that was given, remember that x squared plus y squared is r squared. And so we're talking about 1 less than or equal to r squared less than or equal to 4, which then simplifies to 1 less than or equal to r less than or equal to 2. You still need geometry to think about theta here. So they asked us for the volume between the cone and this ring in the xy plane. So that volume is going to be given by the integral of the equation, which gives the surface over the region that forms the base of the volume that we're trying to find. So we had a theorem a while ago that said if you want the volume between some region of the xy plane and a surface, you integrate the equation that gives you that surface over that region. Here we're going to express the region in polar, so we're going to have an r dr d theta expression. R is going from 1 to 2 here, and theta is going from 0 to 2 pi. My integrand is just r. So x squared plus y squared would have given me r squared, and the square root of r squared is just the single linear term r here. So this is what the volume integral simplifies to, and again, this couldn't be easier for one of the integrals that we're doing here in Calc 2, or Calc 3 I mean to say. It's just a integral of a polynomial over a rectangular region. So I get r squared, the antiderivative of r squared is 1/3 r cubed, r is going from 1 to 2. That's going to give me 8/3 minus 1/3, which gives me 7/3, and then theta, the integral of 1 with respect to theta, as theta goes from 0 to 2 pi, gives me another factor of 2 pi, so that I get 14 pi over 3 for the answer. And now I want to introduce another theorem. This is just a matter of computational simplicity. It's just going to make certain things notationally a bit simpler. It's something that I could have introduced at any point in the course, but I'm annoyed with myself for not having it at this point, so I'm going to go ahead and introduce it so I can make use of it as we're discussing these problems. And you may like it as well. It does help to simplify the expression of certain integrals. So what it says is that if you're taking either a rectangular integral or a polar integral, we've got an expression for both, if your limits of integration are all constants, so my a, b, c, and d versus my alpha, beta, a, and b down here, and if your integrand factors into one function of just one variable and then another function of just another variable. So this is the key point here. You have to have constant limits of integration, and your integrand has to factor into two functions, each of which depends only on a single variable. Then you can actually pull the integrals apart in this way. So I'm going to have the integral from a to b of just f dx and the integral from c to d of just y dy. What we're doing here really is I can take this inner integral, the inner integral is with respect to y, my function of f there is a constant. I can pull that function of f across that integral just like I pull constants across integrals. I did it here with the 7/3. And then I've got my integral from c to d gy of dy with respect to dy. That's all in a constant with respect to dx, and I can pull that constant out across the outermost integral here so that the two end up standing just next to each other. So this is legal, and likewise if you're doing it in polar, if your limits of integration are all constant and your integrand factors into one function of r times one function of theta, you can disentangle them in this way again and just have the two single variable integrals multiplied together. And to hit this caveat once more, it only works if your integral can be factored in this way, and it only works if all limits of integration are constant. So for example, in the problem we just had, we had this 1/3 r cubed dr and then the 0 to 2 pi d theta. I could pull that apart and have my integral with respect to r multiplied times my integral with respect to theta. And we could continue and get the same answer that we did in the formulation shown above. Alright, so now we're just going to do some sample problems for the rest of the lecture. I'm going to throw problems at you. I want you to pause the video, work on them, and we'll come back together to see a solution. And this is meant to be an opportunity for you to work on these metagame skills involved in math class, where it's one thing to know how to use different tools, it's another thing to know which tool is appropriate for a given situation. So instead of only seeing certain integrals that come during certain sections of the course where we're studying that type of integral explicitly, so you know that that's the type of procedure that you're going to use, I want to now wrap up our discussion of 2D integrals by just throwing a bunch of problems at you, having you decide which techniques are appropriate, and attempt to complete the problem using those techniques. So for the first sample problem, I'm going to ask you to find the double integral over a region R with the integrand equal to sine of x squared plus y squared. And R is going to be the portion of the unit disk having radius 2 centered at the origin, and I want that portion of this disk that lies in the third quadrant. So go ahead and pause the video, give that some thought, and we will present a solution presently. Alright. So my region here is a circular type region. We've got a disk of unit 2 centered at the origin, and we want the portion of that disk that lies in the third quadrant. So this is looking like polar to me. It's also worth noting that if I look at my integrand also gives me clues that polar is going to be the preferable coordinate system in which to perform this integral, because my integrand here is going to simplify to a sine of r squared in polar. And I'll also introduce this extra factor of r from my dA expression, and that's going to allow me to compute this using u substitution. So even if you didn't see that far ahead that there's a u sub involved, just seeing the x squared plus y squared should sort of start ringing some alarm bells and letting you know that this might be a polar type problem. And certainly with the region having a circular nature and the integrand suggesting polar variables, we're definitely going to proceed here in polar coordinates. So to describe my region R in polar, it is a portion of the unit disk centered at the origin of radius 2. The disk centered at the origin of radius 2. The disk centered at the origin of radius 2 is given by the equation 0 less than or equal to r, which is less than or equal to 2. And then I further specify that I only want the third quadrant of this disk, the third quarter, the southwest quadrant, by letting theta go from pi to 3 pi over 2. Again, remember, take a little stick, a little line segment, anchor one point of it, one end of it at the origin, extend the other end out along the positive x-axis, grab that other end and start rotating it counterclockwise. That tells you what theta does. And this region doesn't begin until theta gets to pi, so on the negative x-axis, and it ends once theta is rotated around to 3 pi over 2. So swinging that little pinwheel looking stick around, I'm going from pi to 3 pi over 2 to describe my region R, from the negative x-axis to the negative y-axis there. So with that having been determined, my double integral over this region of this integrand is going to look like the integral from pi to 3 pi over 2, the integral from 0 to 2, sine of x squared plus y squared becomes sine of r squared, and my dA expression is r dr d theta. I'm going to use the theorem we just discussed and pull this integral apart. I've got my integrand as a function of r sine of r squared, times the function of theta, where the function of theta is just the constant function 1. And because all of my limits of integration are constant, I can pull the integral apart, the double integral apart, into a product of two single integrals in this way. The first one's easy. You're just going to get theta as the antiderivative and plug in the limits of integration. For the second one, we're using a little u sub, as we mentioned earlier. The antiderivative of sine is negative cosine. We switch back to our original variable before plugging in the values and rearranging things a little bit to write it more simply. I'm coming up with pi over 4, 1 minus cosine of 4 for the final answer. And it's worth noticing here again explicitly that this extra r that we introduced through our dA expression, because we moved from rectangular to polar, that introduced a factor of r, and it was that factor of r that allowed us to make use of u substitution. We needed that factor of r to solve this integral in terms of u sub. If I just had the integral of sine of r squared dr, I don't have a good way to do that. I might have to use a Taylor polynomial or something, a Taylor series. But with this extra factor of r, I can make use of u sub. Alright, let's have you do another. So here's a problem. My integrand is x e to the y. We're integrating over a region D, where D is given by all the xy pairs, such that x is between 0 and 1, and y is between 0 and 2. Give that some thought. Pause the video and attempt the integral, and we will speak of it momentarily. Alright. Oh, pardon me, folks. It has been a long week here trying to get these online classes rolling. So, what are we doing? We're going to compute this integral. So D here is already given as a Cartesian rectangle. It's as simple as it could be. There's no need to bring out the heavy guns for this problem. We don't have to mess with polar. We don't have to try to change the order of integration. There's nothing much going on. This is as simple as our problems get in this course. The problems of this type get. So here's D sketched, just for the heck of it. But I'm going to stick with Cartesian. I'm going to write it as a dy dx integral. There's no real preference. You could write it as a dx dy. Fubini's theorem says they're equivalent. Y was going from 0 to 2, and x was going from 0 to 1. Is that right? Yeah, y 0 to 2 and x 0 to 1. And then my integrand is a function of x times a function of y, so I can factor this out and write it as two single variable integrals multiplied together. They're both relatively simple. One's a polynomial, the other is the exponential. And I can solve and simplify. So that was an easy one. It's common for students to, like, once you've studied a bunch of high-powered techniques, you start off studying the easy stuff, you move through the course, you study the high-powered techniques, you obsess a little bit about the high-powered techniques because they're generally more complicated, and then you're worrying about those so much that when you get to an exam, you're prone to try to use them where you don't even need them. So it's good to be able to recognize when the problem is a simple problem, actually, and uses the earlier material from the course, as was the case here. Let's do another one. So sample problem, here is an integral. I ask you to find it. Nothing more is said. All right, let's see what we got here. So the inner integral here is stumping me a little bit. Looking at this inner integral, I'm integrating with respect to y. I've got the square root of y times e to the y. I'm not going to be able to make use of u sub. I'm not going to be able to make effective use of integration by parts. I'm not sure how to proceed there. I also noticed that my limits of integration aren't constant. At least one of them is not. The lower limit for y is not a constant. So this is going to be either a type 1 or a type 2 region, and maybe by switching the order of integration I can simplify the problem. So we're going to attempt that. I don't know what else to do, so let me try to switch the order of integration. We can sketch the region. One thing you might think is, let's sketch the region and see if it looks nicer in polar. But it does not. It's got this quadratic nature to it. It's got these two rectilinear curves here, the x-axis, the y-axis, and then the line y equal to 1. And then it's got the y equal to x squared curve here, so it doesn't lend itself well to a polar representation either. So instead we are going to try to re-represent it. So I'm looking at the integral as it was given. I see that x is going from 0 to 1. I write that down. I see that y is going from x squared up to 1. I write that down. I sketch the region. So I sketch the xy plane. X going from 0 to 1 is easy. I draw my dots for where x is going to live to give me the interval where x lives. And then as x slides from 0 to 1, my y values are going from the curve y equal to x squared, that's the lower curve, up to the upper curve y equal to 1. So we're going from y equal to x squared here up to y equal to 1. And that's why I'm shading in the upper portion of this box that I've drawn. And now I'm going to re-represent that as the other type of region. That's a type 1 expression for this region. To re-represent this type 2, I have to recognize that y needs to go from 0 up to 1 on the y-axis. And then for each of those y values, as my bead slides from 0 up to 1 on the y-axis, my x values need to go from the y-axis over to this curve, which is going to be the right-hand curve here, the quadratic-looking object. So the y-axis is x equal to 0. That is my left-hand curve for x, my left-hand bound for x. And the right-hand bound for x is still this equation y equal to x squared, but I need to solve it to write x as a function of y. So I get x equal to the square root of y for the right-hand bound. And again, it's the positive square root because my x values are positive here. We're on the right half of the plane, meaning x values are positive. Sorry about that. So this is what this region looks like as a type 2 region. Now I can take the integral as it was given to me, and I can rewrite it as a different iterated integral where I've reversed the order of integration, and it's caused the limits of integration to change. And now I can integrate the inner integral relatively easily, or actually quite easily, because the integrand is constant with respect to x. So I actually just pick up a factor of x. X is going from 0 to root y. Plug in that extra root y, and the square of the root is going to give me y. Plug in 0 and get 0. So I'm left with the integral from 0 to 1 of y e to the y dy. And this is a straightforward integration by parts problem. I have the schema laid out here for this integration by parts. But we're going to have y e to the y from 0 to 1 minus the integral of just the exponential from 0 to 1. This is going to give me an e minus 0 for just e. And then integrating e to the y gives me e to the y. Evaluate from 0 to 1. The two e to the 1 expressions cancel, and my answer is just 1. So this was one where we had to proceed in Cartesian, but we were integrating over a more general, which is to say non-rectangular region, and we had to reverse the order of integration in order to make use of integration by parts, in order to introduce a new factor that allowed for integration by parts. Alright, another sample problem. Let's let R be a rainbow-shaped region, and we're going to create this rainbow-looking region by taking the space between the circles x squared plus y squared equals 1 and x squared plus y squared equals 2, and we want the portion of the region between those two circles which also lies above the x-axis. And then I changed my mind about what I wanted your integrand to be, and I've asked you now to find the double integral over that region of this integrand, e to the root, the 1/2 power of x squared plus y squared. So pause the video and give it a go. Alright. So what we're looking at here, let's draw the region. We're looking at the region where in polar, it's going to be in polar, best described. Again, this is an instance where both the region itself, once we draw it, and the form of the integrand as given suggests that polar is going to be the way to go. So, looking at this region, I've drawn it here. We've got the upper half of the circle of radius 1, and we've got the upper half of the circle of radius square root 2. And so r is going to be going between 1 and root 2 from the inner circle to the outer circle. And because we only want the upper half, we're only letting theta go from 0 to pi, so that my little swinging bar can swing from the right hand, or the positive x-axis, up through to the negative x-axis. So with that formulation of the region, we can write this double integral we've been asked to find as an iterated integral given in polar. My exponential integrand just becomes e to the r. Again, this is the square root of r squared in polar, so I just get e to the r, and I introduce another factor of r with my dA expression. R is going from 1 to root 2, and theta is going from 0 to pi here. This is an instance where I've got all constant limits of integration, all 4 are constant, and my integrand looks like r e to the r times 1. So I can pull that apart and write it as the product of 2 single-dimensional integrals. This one is trivial, you just get pi minus 0 as pi. For this one we're going to do integration by parts. I have glossed over the details of the integration by parts application here. If you have any questions, I'd be happy to answer them. But we do have an example of a similar problem just a few moments ago. So this is the expression that you get for this integral. The root 2 and the 1, we're going to have to plug stuff in, and it gets a little bit hairy. But once you cancel everything that can be canceled and simplify the expression a bit, it should come out to be pi root 2 pi times root 2 minus 1 times e to the square root of 2. This parenthetical expression is about 0.4 and change, if I'm not mistaken. So that's how that one works. So several different examples, not to say that this is an exhaustive list of all the types of problems you could see, but these were definitely lots of different types of problems I can throw at you. I certainly don't have to tell you which coordinate system is best or what techniques you're going to use. Do you need to change the limits of or the order of integration, for instance? But it's your job to look at the problem and try to come to some decision about what techniques that we've used are appropriate for this problem and what coordinate system is best at handling the region under consideration. Alright, thank you, folks. I will talk to you again on Tuesday. Have a great weekend, everybody.